In this video, we're going to consider the various tests for seeing if a series is convergent. But first, I want to make sure that we remember the difference between a convergent sequence and a convergent series. So in a convergent sequence, we could have something like this. We could have 1, comma, 1/2, comma, 1/3, comma, 1/4, comma, 1/5. And as we go along, we can see that this converges to 0. Now this is in contrast to a not convergent series. So if we consider our harmonic series, the difference is instead of being a sequence, it's now a series, which means we're going to add all these up. So we have 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus ... And that actually heads to infinity. We studied this one. We knew it was the sum of 1 over n. And we know that this diverges. You might recall we did a whole spreadsheet and we saw that the sum just keeps getting bigger and bigger and bigger. Now in contrast, we might have the following convergent series. And that is the one that looks like this. We could have 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1 over 32 plus ... And you'll recall that this is the one that is 1/2 to the nth power. And we drew a picture of this when we first studied these. And we said, oh yeah, I'm going to first take half. That's half of the area of this. And then I'm going to add 1/4 of the area. And then I'm going to add 1/8, and then 1/16, and then the 32nd. And we can see that in the square that, by the way, was 1 by 1. When we're all said and done, that infinite sum is actually going to equal 1. We're just going to keep adding in little bits. And what's happening here is it's getting adding terms small enough, fast enough that the sum equals 1. Just as a reminder here, we remember we have that sum formula where we have 1/2 over 1 minus 1/2, which also gives us the sum of 1. So a couple of different ways of seeing this. So remember, a series means that we're adding it, and in order for a series to converge, the terms as we go to infinity have to get small enough, fast enough for that to work. All right, so let's talk about which series we should recognize right away. So a geometric series is one of the first ones we should recognize right away. A geometric series is any series that can be written in the form the sum of a times r to the n, and it converges anytime the absolute value of r is less than 1. The next type that we should know right off without having to think so hard is any p-series. So a p-series is anything with the sum of 1 over n to the p, and this converges anytime p is greater than 1. By the way, we also know that this one up here diverges otherwise. And same thing here. It converges when p is greater than 1. It diverges otherwise if p is less than or equal to 1. The other one that we should recognize right away is an alternating p-series where the terms are decreasing with decreasing terms. And when I'm talking about the terms decreasing, I'm talking about the absolute value of the terms decreasing. So this would be anything that could be written in the form -1 to the n over n to the p. All of those are going to converge as long as the positive portion is going to 0. So the limit as n approaches infinity of 1 over n to the p. So I'm just looking at the positive portion of this goes to 0. All right, so those are the quick, obvious ones that we should just know. And so now we get a lot of them where they look very similar to that. So what can we do if they look similar? Well, if we're less than a converging series, it will converge. It will converge. Also, if it's greater than a diverging series, so greater than a diverging series, it will diverge. Now, sometimes they don't come out quite so convenient, in which case we use our limit comparison test. And the limit comparison test said, well, if I've got two series that look similar and I know about one of them, I can take the limit as I go to infinity and compare the two. And if when I compare the two, it equals c, some positive number, that means that they behave really similarly as you go to infinity. So as you go to infinity, the only difference between them is some constant. And if this happens, they both diverge or both converge. So just a reminder, in this case, one is a known one. It doesn't matter which is which, but this is our known series, and the other is the series that we're testing, series being tested. All right, so far we've looked at the ones we know about, particularly our piece series and our geometric series, and we've talked about what if it looks like one of them. Well, what happens if it doesn't look like one of them? What are the other tests we should know? Okay, the absolute first test, really in any case, is if the limit as n approaches infinity of a sub n does not equal 0, it diverges. You should always take a look and see whether your terms are going to head to 0. And in doing that, it's also worthwhile to know that, let's see, exponentials, let's try that, there we go. Exponentials grow faster than polynomials. And factorials grow faster than exponentials. That's because in an exponential, you keep multiplying by the same number. So maybe you keep multiplying times 2, times 2, times 2, times 2. Whereas in a factorial, you keep multiplying by a number, but the number you're multiplying gets bigger. All right, our second one that we should know is our integral test. So we should know that if the integral of f of x converges, then the sum of f of n converges. We would use the same limits as the sum. And also, if the integral of f of x diverges, then the sum of f of n diverges. So we've got that nice little relationship, and this, of course, is the integral test. Third, anytime we have an alternating series, we should remember the test for checking there. And in an alternating series, there are two things that have to happen. The terms get progressively smaller, get smaller approaching 0. And again, when we're looking at this, we're looking just at the positive portion. So the terms are approaching 0, and each term is getting smaller than the previous. So each term is smaller than the previous. And again, like I said, in this, we're actually looking at the absolute value of the term when we do that. All right, so that leaves one other test that we should know, which of course is the ratio test. The ratio test is always a good go-to test, but it does take a bit of work. And so just a memory that in the ratio test, we're taking the limit as n approaches infinity. We are taking the ratio of the n plus 1 term over the nth term. And if that is less than 1, it converges. If it's greater than 1, it diverges, and if it equals 1, well, you got to look for another test. Remember, if you see a factorial, this is your go-to test. So this is the go-to test for factorials. And this is the test that shows up all of the time, or very frequently rather, on free response questions.